Salutations, class. I'm feeling very patriotic today because Lesson 14 is on Independence Day. Fantastic. Let's get right into it. Any unrelated events are independent. For example, it rains on Mars tomorrow versus a coin lands on heads. Those are independent. One doesn't affect the other, or so they have you believe. The formal definition, A and B are independent events if and only if the probability of the intersection is the probability of A times the probability of B. That's just the definition. Example, if the probability that it rains on Mars is 0.2 and the probability of heads is 0.5, then the probability of rain on Mars and heads is, because they're independent, P of R times P of H is 0.1. Remark, if P of A equals 0, then A is independent of any other event. And remember, we have discussed the fact that you can have an event A with probability 0. Now, events don't have to be physically unrelated to be independent. Here's an easy example. Let's toss a die, and the event A will be, we observe an even number, 2, 4, 6. The event B will be that we observe 1, 2, 3, or 4. So A intersect B is obviously the set 2, 4. This implies that the probability of A is a half, or that we observe an even number. The probability of B is 2/3. That's the probability of observing 1, 2, 3, or 4. And the probability of A intersect B is 1/3, because we have two elements in A intersect B, namely 2 and 4. So you can see that the probability of A times the probability of B equals 1/3, and the probability of A intersect B equals 1/3, and so the guy on the left equals the guy on the right, and that implies that A and B are independent. Theorem. This is a really natural interpretation of independence. This is kind of how I think of it. In plain English, if I know that A and B are independent, then the probability of A doesn't have any dependence on the fact that B occurs or doesn't occur. Okay, so let's take a look. Suppose the probability of B is greater than 0. So it's some event of non-trivial probability. Then A and B are independent if and only if the probability of A given B equals the probability of A. So just like I said, whether or not B occurs has no effect on the probability of A. Here's the proof. A and B are independent if and only if, by definition, the probability of A intersect B equals P of A times P of B. If and only if the probability of A intersect B divided by the probability of B equals P of A. Now, how did I do that? I just moved over one term, probability of B, which had a probability greater than 0, so dividing was legal. Now, you'll see that that last equality, the left-hand side, is the definition of the probability of A given B. We are done. So again, if A and B are independent, the probability of A does not depend on whether or not B occurs. Here's a bonus theorem. A and B are independent if and only if A and the complement of B are independent. So I'm going to actually prove this. This is sort of a bonus proof. We're only going to prove it in the left to right direction because the left to right, or the right to left direction follows trivially after that. Okay, so I'm only going to do it one way. Note that. Remember that old thing, the law of total probability? I'll evoke it here as well. The probability of A equals the probability of A intersect B bar plus the probability of A intersect B. Now, this follows because A can be decomposed into the part that intersects B and the part that doesn't intersect B. They are disjoint, so you add the probabilities up. Okay? Thus, the probability of A intersect B bar equals the probability of A minus the probability of A intersect B, that's trivial, equals the probability of A minus the probability of A times the probability of B, because A and B are independent. That's by assumption. That equals the probability of A times 1 minus the probability of B. All I did, I just pulled out P of A. And by definition, that's the probability of A times the probability of the complement of B, because that's 1 minus P of B. Okay? And we're done. The upper left-hand side equals the lower right side. And that's what we wanted to prove by definition of independence. So that's kind of nice, easy little proof. One thing that I always tell people, this is sometimes a source of confusion, is that don't confuse independence with disjointness. Here's the theorem. If the probability of A is greater than 0 and P of B is greater than 0, then A and B can't be both independent and disjoint at the same time. So do not confuse them. Here's the proof. Suppose A and B are disjoint. That just means that A intersect B equals nothing. Then the probability of A intersect B is 0, which is less than P of A times P of B, because we're assuming, by definition, P of A and P of B are both greater than 0. So the intersection does not equal the product. So they're not independent because they're not equal. Similarly, going the other way, independent does not imply disjoint. So there you go. It's a nice little proof. Remark, in fact, independence and disjointness in some sense are almost opposites. If A and B are disjoint and A occurs, you have information that B cannot occur. So you've actually got, it's negative information, but it's information that B can't occur. So therefore, A and B can't be independent. Okay, so we've talked about A and B being independent. Let's talk about an extension to more than two events. Definition: A, B, and C, all three of them are independent if and only if, well, the triple intersection factors to the triple product. The probability of A intersect B intersect C equals P of A times P of B times P of C. So that's what most people would think. But a lot of people forget you also have to add this next condition. All pairs of A, B, and C are independent individually. So probability of A intersect B equals P of A times P of B. Probability of A intersect C equals P of A times P of C, etc. So the triple intersection has to factor, and all double intersections have to factor. Does that make sense? Yeah. So you have to be very, very, very careful about that. So what I'm going to do is show you why you got to be careful. Here's an example. Condition A, the triple intersection, is not enough. Okay, so let's see what I mean by that. Suppose I'm doing one of these D&D dice tosses, and so the sample space of the 8-sided die, because I'm a little elf, is just 1, 2, 3 up to 8, each with probability 1/8. Let's define the events A equals 1, 2, 3, 4, B equals 1, 5, 6, 7, and C equals 1, 2, 3, 8. So just real quickly, the intersection of A, B, and C is the element 1. Therefore, the probability of A intersect B intersect C, that is probability 1/8. Meanwhile, the probability of A is a half, the probability of B is a half, probability of C is a half, because they all have 4 elements. You multiply those together, you get an 1/8. So that first condition A is satisfied. Yay, fantastic. But B is not satisfied. For instance, A intersect B, I constructed this in a certain way, is just the element 1. Therefore, the probability of A intersect B is 1/8. This does not equal the probability of A times the probability of B, which is a quarter. Therefore, A and B are not independent, and you can see I have my funny little contradiction sign there, which means I've established a problem. Stay vigilant, because condition B, the double intersection, is by itself not enough either. So example, let's let S, the sample space, equal 1, 2, 3, 4, each with probability 1/4. I'm going to let A equal 1, 2, B equals a set 1, 3, C equals 1, 4. So the probability of A intersect B equals a quarter, equals the probability of A times the probability of B. So you'll look at that. The probability of A intersect B is the probability that you see just a 1, which is a quarter. The probability of A is a half, probability of B is a half. So P of A intersect B equals P of A times P of B. Same deal with A and C intersecting and B and C intersecting. So without going into every single detail, condition B is fine. However, condition A is not. The probability of A intersect B intersect C, well, they all intersect with the element 1, and so that probability is a quarter. That is not equal to an 1/8, which is the product of all 3 of the individual probabilities. Bang, contradiction. You got to be careful. Let me now give the general definition, and don't be afraid. This is not a big deal. Suppose A1 through AK are events. They're going to be independent if and only if that entire intersection, probability of A1 intersect A2 intersect ... intersect AK, equals the entire product. P of A1, P of A2 ... P of AK, and here's the catch, all subsets of A1 through AK are independent. So that's what we did before. We had three things, and not only did the triple intersection have to work out, all the double intersections, all the subsets had to work out. Okay, let me informally tell you what the phrase independent trials means. It means I perform n trials of an experiment such that the outcome of one trial is independent of the outcomes of all the other trials. For example, flip 3 coins independently. One doesn't affect the other. The probability that the first coin is heads equals a half. You don't worry about the other two coins since they're independent of the first. And in fact, the probability of the second coin being heads is a half because they're independent of each other. In addition, the probability that the first coin is heads and the third coin is tails, since everything's independent, multiply them together. Probability the first coin heads times the probability the third coin tails is a half times a half equals a quarter. So obviously, for independent trials, you just multiply the individual probabilities, which is what we did there. Really easy. I'm going to do one last example in this lesson. Let's flip a coin infinitely many times where each flip is potentially, well, it's independent of all the other ones. So flip a coin infinitely many times. Each flip is independent of the others. So I'm going to let P sub n be defined as the probability that the first head is obtained on the nth trial. So that means I observe tails, 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 n minus 1 tails before I see the first head. Since they're all independent, I multiply them out. P of t, P of t, P of t, n minus 1 times finally the successful probability of heads. Each one of those has probability 1/2. I'm multiplying the tails n minus 1 times the heads 1 time, so I get an overall probability of 1/2 to the nth power. Therefore, the probability that I see heads eventually is the sum of every single Pn. Remember, P sub n is the probability that I see heads for the first time on the nth trial. So I add up every possible value of n, and eventually I get this interesting result. This is the sum from n equals 1 to infinity of 1/2 to the n, and I happen to know from calculus class that that equals 1. In plain English, that means I'm eventually going to see a head. Okay, great. So now we know what independence is. We've got some idea of conditional probability, and I'm going to talk more about conditional probability in particular when I talk about partitions and the law of total probability in the next lesson, which is a really interesting lesson leading up to the fantastic Bayes theorem. So we'll see you then.